speaks about Cauchy-type integrals in multivariable complex analysis.
Thank you, Yuri, very much. And I wanted to take this opportunity to thank the organizers of this wonderful program in complex analysis that has been going on for a few months. I am learning many, many new things. And I would also like to thank the organizers of the workshop for giving me the opportunity to tell you a little bit about mathematics that is a little bit off the mainstream for a group of mathematicians who work primarily in fluid dynamics. So I will give a survey of my decades-long collaboration with Elias Stein, who unfortunately passed away a few months ago, as a few of you may know. And so this is also going to be a way to honor his memory by telling you a little bit about our joint work. So let me give you, before we actually get started, I want to give a little bit of an overview of what's going to happen in this hour. So we start, in fact, about half of my talk will be in one complex variable, in spite of the title, which I should have amended. So we start with a domain in the complex plane, so one complex variable. And we work with functions that are holomorphic in the domain. So for me, holomorphic is the same as complex analytic. And it's continuous up to the boundary. And that's the typical notation. And so the reference results here are the classical Cauchy theorem for analytic functions, which allows for contour deformation, so very useful tool in applied mathematics in fluid dynamics. And the Cauchy integral formula, which allows you to recover the information about data on the interior of the domain, but just knowledge of information about that data on the boundary of the domain, so from a much smaller set. So now, these two objects have two main assets from my perspective. First of all, the integration kernel, the Cauchy kernel, if you view it as a function of the output variable z in the domain, since w is the integration variable which takes place on the boundary of the domain, so that's a holomorphic function as a function of z for each fixed w on the boundary. Secondly, the Cauchy integral, or kernel, if you will, is meaningful for most contour shapes. It's a universal kernel. The effect of the particular shape that you're integrating against is just that you're taking this universal kernel and restricting it to the shape. But it's the same kernel all the time. It has, however, one major drawback, and that is the Cauchy kernel, the Cauchy integral, lacks a good transformation law under conformal maps. And this is a rather general statement. I will be more specific later. But the general idea is that if there is something good I can say about the Cauchy integral on a circle, is there a law that will allow me to transfer that same kind of result to the Cauchy integral over an arbitrary curve? So that, unless the curve is very special, unless you're talking about a line and a circle, that's very difficult to do because there is no transformation law under conformal maps. OK. So this brings up three questions which are going to be the focus of this talk. And as you can see, the first question is actually in one variable. Is there another integration kernel that retains what I called the main assets of the Cauchy kernel, but in addition has a good transformation law under conformal maps? That's question one. Question two, and this is in higher dimension, complex dimension 2 or higher. Is there an analog of the Cauchy kernel that retains the main assets that we described in the previous slide for functions that depend on 2 or more complex variables? And then in any dimension, 1 or higher, do the answers to this previous question depend on analytic, sorry, that's a typo, that analytic or geometric properties of the ambient domain? So on the regularity of the curve of integration, or somehow the geometric shape. Scott this morning was talking about convex bubbles, non-convex bubbles. As you will see, we will run into that same kind of questions. OK, so let's take a closer look. So there you go. That's the Cauchy integral along the boundary of a planar domain. And we want to regard it as a singular integral operator. So this means that, as opposed to what we teach in first year, in undergraduate complex analysis, Z is no longer going to be a point inside the domain. It will be a point on the boundary of the domain. So we'll have, if this is our domain in the plane, you have a variable of integration W. In the classical setting, Z sits inside, but now I want to take Z on the boundary. And so the kernel becomes singular because W will be, at some point, will be equal to Z. So in that sense, in that case, then one interprets the Cauchy integral as a principal value integral. So the classical way is to fix your Z, bite a little, let me put another Z here, because I'm going to save this for later. You're going to bite a little piece away from Z, epsilon. So you have deformed your contour. And then for that contour, the integral makes sense in the classical sense. Then you let epsilon go to 0. And if you're lucky, there is a limit. And if that limit exists, which it does, you call it principal value. I wanted to point out that there is also another approach which we have exploited, and it turned out to be very useful in higher dimension. Because in higher dimension, the geometry of the boundary is anisotropic. There are special tangential directions that play a special role. And so taking away a little sphere is not a good idea. You have to work with more exotic geometric objects. And so instead of doing that, you can exploit the Cauchy formula. So this is your Z on the boundary. Well, you just go a little bit inside along the normal direction, perfectly well defined, Z epsilon. So now Z epsilon is inside. Eventually, Z epsilon will tend to Z when you send epsilon to 0. But now you can apply the Cauchy formula to Z epsilon, because that's an interior point. And so you simply add and subtract f of Z epsilon, but writing it in two different ways. And so now you have this new integral. And if you make the right assumptions on f, so your holomorphic function f is not just continuous up to the boundary, but has some more extra continuity, for instance, the class C alpha, or the class C1. So then what happens is that the numerator in blue here will make up for the singularity of the denominator. And so what you have is a non-singular integral now. And what you have to do is prove that the right-hand side has a limit when epsilon tends to 0. And that limit will be the analog of the principal, in fact, equal to the principal value integral. So that's another way of thinking about it. So here is the landmark result. And I'm stating it in plural, results, because the full result was obtained in 2 stages by 2 different groups of people. Calderon first, Alberto Calderon, who, by the way, started off as an engineer, in the case when the constant m there is small, and then for arbitrary size m later by Kaufman, McIntosh, and Meyer. And so the landmark result says the following. Suppose that your domain is the boundary of a Lipschitz curve. And so this means that you can, at least locally, here we have it globally, describe it as the graph of a function a of real variable that is Lipschitz with constant m. So then the conclusion is that the Cauchy integral interpreted as a principal value or a singular integral operator is bounded in the Lebesgue space LP for p in the full range from 1 to infinity with respect to arc length measure. This was a watershed moment when this theorem was proved in the harmonic analysis community. And I want to try and give you a sense of the reason why working with a Lipschitz curve was such a big deal. So here is our graph. And at the moment, I'm not making any assumption on the graph, okay? And I'm taking 2 points on the graph, W and Z. W is parameterized by X and Z by Y. So 1 over W minus Z, the Cauchy kernel, is written like this. Okay. So now formally, I'm going to factor X minus Y out. And I have this. So again, formally, I'm going to think of this square bracket here as the sum of a converging geometric series. So I have 1 over x minus y, and now I have the summation for j from 0 to infinity, but I'm going to pull out j equal to 0. And then I have j from 1 to infinity. And then this. Hopefully I haven't made any mistakes. So how am I going to interpret this? Remember, you have 1 over x minus y here. So this is precisely, this first term here is precisely the kernel of the Hilbert transform on the real line. And this is what I'm going to call an error. So what have we learned from this formal argument? We have learned that the Cauchy kernel can be thought of as the kernel of the Hilbert transform on the Cauchy kernel for an arbitrary curve is the Hilbert kernel on the real line plus an error. So far, so good. So now, if the error is small, then my Cauchy integral is pretty much the same as the Hilbert transform, which is the archetypal singular integral operator. We know everything about it. The size of the error depends on the regularity properties of the function a, which encodes the regularity of the curve. If a is a smooth function, that is to say, if the curve a, the curve over there is smooth, then these quantities will be small and the error will be made small. So in effect, the principal singularity of the Cauchy integral is just the same as the principal singularity of the Hilbert transform. Now, in mathematical, in analysis terms, this means that A can be as good or as bad as the class C1 alpha. So of class C1 with first derivatives continuous C alpha, Hölder alpha. The threshold for the failure of this naive argument is the case, and I want to record it here to keep this in mind, is the case when the curve, the function a is just of class C1. If a is just of class C1, the error is no longer negligible, and you need to make an argument in order to justify the statement that this is the principal singularity. But the argument is still rather reasonable. It's by approximation. So the first situation where there was no way to adapt this naive, decomposition to get a proof of regularity was the Lipschitz case. And that's why this result of Calderon and then completed by Kaufman, McIntosh, and Meyer was such a big deal. So we have a sense of how the regularity properties of the Cauchy integral for a curve are tied up with the regularity of the curve. Okay, so here is a remark to keep in mind for later. The Cauchy integral for a Lipschitz curve is the prototypical Calderon-Zygmunt operator, for those among you who are familiar with this lingo. And a crucial feature of Calderon-Zygmunt operators is that being bounded when in LP for p equal to 2 is equivalent to being bounded in LP for p in the full range between 1 and infinity. That's a crucial, this is a feature of the Calderon-Zygmunt operators. So this result of Calderon and the other people concerning LP regularity of the Cauchy integral for a Lipschitz curve had a huge impact in harmonic analysis over, starting from the 1980s. Elliptic linear PDEs, new techniques for studying singular integral operators. That should be analytic capacity. When you change a word with the command find, and then it changes everything, whereas it shouldn't change one or two. Analytic capacity, the Vitushkin conjecture. But what I'm interested in here is the impact of that result in complex analysis in one and several variables. I will mention here, I just put in the Debar problem because I have learned that it can be interpreted as a Riemann-Hilbert problem. And so, since there are ways of, as we know, many people in this room know, of solving the Debar problem using Cauchy integrals, if you have estimates for the Cauchy transform, that translates into estimates for the solution of the Debar problem. But that's all I will say about the Debar problem. And I want to focus instead on the applications of two orthogonal projections of the Hilbert-Lebesgue space L2 onto spaces of holomorphic functions that are associated with a bounded domain in one or higher dimension. And in particular, there are two such projections. One is the Szego projection, which is the orthogonal projection onto the holomorphic Hardy space. And the other is the Bergman projection, about which I will say nothing. It's the orthogonal projection onto another closed subspace of another Hilbert L2 Lebesgue space. So let's focus on one such projection. So I remind you that the holomorphic Hardy spaces are spaces of functions that are holomorphic or analytic inside the domain, and then satisfy some sort of uniform LP boundary growth as measured by an exhaustion of the domain by a family of subdomains. And if the condition is true for one family of exhaustions, then it will be true for any family. So a typical example, or maybe not so typical example, of a member of HP is a function that is analytic in the domain and continues up to the boundary. But HP is a much richer space. You have functions in HP that have zeros on the boundary of the domains with infinitely many zeros inside that accumulate to the boundary point, for instance. It turns out that HP is a closed subspace of the Lebesgue space, and so P equal to becomes doubly special, because now you have that H2 is a closed subspace of a Hilbert space. And classical functional analysis guarantees the existence of a unique orthogonal projection operator onto the closed subspace. And that is known as the Szego projection. Now here, orthogonality is measured with respect to the arc length measure for the boundary. Okay, so sigma is always going to be arc length measure for me. And I remind you that there are various characterization of the notion of orthogonality. One is that the operator is self-adjoint, and the other one is that the operator has minimal L2 norm. Yes? So you have a family of subdomains that exhaust. So the d sub epsilon would be, you know, something like this. Think about your favorite Riemann map and then take the level curves, for instance. Okay, so now, what are the similarities with the Cauchy integral? The Szego projection, just like the Cauchy integral, is an integral operator. Integration against the kernel, the Szego kernel. Just like the Cauchy kernel, the Szego kernel is holomorphic in the output variable z. And you have a Cauchy-type formula. If you start with a data f, which is analytic inside, continues up to the boundary, you can reproduce it by integrating it against the Cauchy Szego kernel. And so, the Szego kernel, sorry, that's another typo, the Szego kernel retains two of the main assets of the Cauchy kernels that we mentioned earlier. Okay. However, it is not universal. It is domain specific. It changes with the domain that you decide to work with. In particular, if you pick the disk, if your domain is the disk, then the Szego kernel is essentially the same as the Cauchy kernel, with a caveat. You see that the reference measures have been changed in that equality. You have the arc length measure, the sigma on one side and the w on the other. So one has to work out, we have to be a little bit careful and extract arc length from dw. That will bring out a factor. And that factor has to be considered as part of the Cauchy kernel for this identity to hold. So now, why is that good news? That's good news because the Zego kernel and projection enjoy a good transformation law under conformal maps, somewhat making up for the lack of universality. And so if phi is a conformal map between two domains, I'm assuming simple connectivity here so that the classical theory goes through. So you can express the Zego kernel for one domain in terms of the Zego kernel for the other domain composed with a conformal map. Plus, and in addition to this, you have some multiplicative weights that are given by square roots of the complex derivative of the conformal map. The classical theory of conformal maps grants that those square roots are well defined. You know, there are analytic branches defined in the domain, so that this expression is meaningful. Yeah.
Is it known under what conditions on the boundary that you have the Zego kernel to be extended to one of its variables across the boundary?
Oh, that's a good question. No. To what extent? Not that I know of. Maybe let us talk afterwards. So, okay, that's a very interesting question, but I don't want to spend time now. But it has to do with the regularity of the boundary. For instance, I expect that if the boundary is smooth, you might be able to have some extension. But, actually, no, I take it back, because the Zego kernel is singular across the boundary. At z equal w, it is always singular. So if you fix a z, then you may be able to extend. But as you change your z, so we need to talk about that. Other questions? OK. So now, more dissimilarities with the Cauchy integral. Remember what we said. We said that a characterization of being an orthogonal projection is to be bounded in L2 with minimal norm. So the Zego projection is trivially bounded on L2. However, in general, it is not a Calderon-Zygmunt operator. And so from boundedness in L2 does not follow boundedness in LP. And in fact, there is a problem that with Eli we have been working on for the past 20 years, which is to study the maximal P range about P naught equal to 2, for which the Zego projection is bounded in LP. Now, the fact that the operator is self-adjoint tells you a little bit about the shape. The shape of the range has to have a certain symmetry. Okay, the two endpoints have to be Holder conjugates. But what is the largest P about 2 for which LP regularity of the Zego projection holds? So the reason why we're interested in this question, because it seems that the size of this range has something to do with the geometry and the regularity of the domain, of the ambient domain. So there is a result of Stevens-Sams. It doesn't prove this theorem exactly, but if you put the pieces together, you get the theorem, which says that if the, so here I have put down a list of various kinds of domains. Think of them as a hierarchy, and you go from the top, which are the most regular domains, to the bottom, which is the least regular domain. Okay? And different people have obtained different results. So if you start with a domain that is rather smooth, class C1, remember right before the threshold of that naive argument before, you get that the Zego projection is bounded in a P for P in the full range, from 1 to infinity. But now, if you pick a domain that has corners, a Lipschitz domain with constant m, then you get for sure LP for P in a range that always properly contains the interval 4/3 to 4. And that range is optimal in the following sense. If you give me a Lipschitz constant m, and then you give me a P naught value that is outside of that range, I'm going to be able to give you a Lipschitz domain with that Lipschitz constant m, whose Zego projection is not bounded in LP naught for the P naught value outside of the range. Now, if you reduce the regularity to a rectifiable local graph, think about a domain that can wiggle a lot and accumulate to one of the axes, say. but still a graph. But now you're not going to be able to stick a wedge of fixed side inside because these oscillations are changing all more. You still retain 4/3 to 4. And if your domain is Alford's regular, a condition that I'm not going to describe other than say that I was really happy yesterday to see in Professor Benamar's talk pictures of domains that indeed are Alford's regular. So when she was showing those the film of the gel that was growing, and it was developing those cusp-like petals, so that's an instant of an Alford's regular domain because it allows for cusps. Or when she was showing photographs of gel that had some kind of cuts in them, there were some cuts. I would describe them as cuts. That would be another instance of a domain that is Alford's regular. In fact, it is chord arc. Yeah?
Question. If you have an inaccessible boundary point,
yes.
would that be the first case Stein considered?
So an inaccessible vanishing chord arc?
Yeah,
like a point, like a disk without a minus.
You have a limit point.
Yes, I have to think about that. Okay, it is a jungle. Let us keep track of those questions and get back to them. And already in 1990, people knew that there are rectifiable domains, which, however, are so bad that the Szego projection is bounded in L2 and precisely in L2. Now, these domains are not given constructively. They're given by conformal map. And so the idea is to construct a conformal map that looks terrible, and then its image will be the bad domain. But you can see that as we reduce the regularity of the domain, the size of this range shrinks. It would be good to know, we don't, if the size of the domain is an indicator of some specific property of the boundary. For a long time, we thought that there was some notion of turning of the boundary curve that had to do with this size, but we were never able to pin it down. So let's talk about now a connection of the Szego projection with the Cauchy integral, another connection. Let's forget the Cauchy integral for a moment and suppose, let's talk in general terms. Suppose that you have another projection T from the Hilbert-Lebesgue space L2 to the Hardy space H2. And projection onto this space, it means two things. If you start with the data which is merely square integrable, the output will be analytic inside, number one. That it means to map into H2. And then it means, once you are into H2, since that is a projection, then it acts as the identity. And so that means that it is producing and reproducing holomorphic functions from their boundary data. So now you have two projections, the orthogonal projection S and another projection T. And so it's very natural, this is an operator theoretic argument, to compare them with one another by composing them consecutively. So you start with T maps into H2, but then S is the identity on H2, so you get this equation. Reverse the roles, same story. Now take adjoints, and remember that S is self-adjoint. So you get this new identity. And now subtract identity number 1 from identity number 3, you get this. Let us solve for the non-orthogonal projection. We get this new operator identity on the Hilbert space L2. So what was Kurtzman and Stein's basic idea that substantiated this general operator theoretic? Very nice argument. The idea was that if in some way the difference of the non-orthogonal projection with this adjoint is somehow better than each of T or T star alone, that means if you have a cancellation of singularities, then you can use that equation above to draw information from one operator to the other. I am especially interested in the second bullet. Suppose you know that the non-orthogonal projection is bounded in L2, or rather, yes, in L2. Can we solve that equation on top for the orthogonal projection? Yes, by, again, a functional theoretic argument, because the difference of T and T star is almost self-adjoint, is Q adjoint. And there are general arguments that allow you to say that if you know that T is bounded, then this operator is invertible in L2. And so you have now an equation, an operator identity in L2, which expresses the orthogonal projection purely in terms of the non-orthogonal one. And so the question is, what about LP if P is different from 2? And this is settings where the results are known. So you have a bounded domain, and now T is the Cauchy integral. So if you know that your domain is smooth, and by that we mean class C2 or better, then the difference of these two operators is the best you can hope for. It takes a function that is merely integrable and maps it to a function continuous on the boundary. It's smoothing operator. So in that respect, under those circumstances, you have that the identity minus the difference of T and its adjoint is invertible with bounded inverse in LP for P in the full range. Now, if you reduce the assumptions to vanishing constant chord arc, which includes the case when the domain is of class C1, then the difference will not be smoothing, but it will still be very good. It will be compact. The operator theoretic analog of the function being uniformly continuous as opposed to continuous. And once you have compactness, and that will hold in LP for all P, again, you get invertibility. And so in these instances, you are able to solve the LP regularity problem for the orthogonal projection in the full range by way of comparison with the non-orthogonal projection. So what happens in higher dimension? I'm afraid that that was the end of the n equal 1 part of this talk. Now we're going to n equal 2 or higher. So at the moment, from now on, we are in 2 complex variables or more. First of all, the notion of Hardy space is taken verbatim from the one-dimensional case. The only adjustment you need to make is that instead of talking about chord arc, now you have to talk about induced Lebesgue measure in this context, Lebesgue surface measure. So again, you have that when P is 2, H2 is a closed subspace of L2. So again, you're guaranteed the existence of the orthogonal projection, the Szego projection. And there is an example for you in 2 complex variables. The domain is the ball. And the Szego projection for the ball in n, I'm sorry, I should have said, so that n should be a 2 there. So you would have to have a 2 minus 1 factorial, so to speak, and 2 pi squared. So, but anyway, there is an almost correct formula for the Szego kernel of the unit ball in 2 complex variables. Now, what's the problem? If you think about that structure of ideas that we have in one variable. Now you have 2 problems. Well, one, there is no Riemann mapping theorem. So you cannot take the ball, you cannot take an arbitrary simply connected domain and presume that there is a one-to-one and onto holomorphic map that maps to the ball. You can't. But even if you were to restrict the attention to those subclasses of domains for which you could map biholomorphically to the ball, you would still be in trouble because when n is 2 or higher, there is no good transformation law under biholomorphic maps. The problem is that square root that was showing in the identity we had before. The reason why we had square roots is because you obtained a transformation law by producing an isometry of L2, 2 1/2, so to speak. You need a square root. Now, in one variable, the theory of conformal maps grants that the square root of the derivative of the conformal map is meaningful. Is in fact in a Hardy space. It is in H2. But in higher dimension, there is no guarantee that you have a uniquely defined square root of the biholomorphic map. So there is no good transformation law. And this makes the study of the Szego projection in higher dimension much harder than the one-dimensional setting. Okay. However, remember that we highlighted in the one-dimensional setting an argument, a little strategy, that did not depend on conformal maps or on transformation laws. That was the comparison with the Cauchy integral. And that argument is dimension free. So in principle, you can apply it to any dimension. And that approach has been pursued extensively for a long time. So let me recap with you what are the key ingredients in this comparison argument. What do you need? You have to have, first of all, a meaningful notion of Cauchy kernel when Z is multivariable. Secondly, this meaningful notion of Cauchy kernel has to be holomorphic as a function of the output variable, Z. Thirdly, the corresponding singular integral operator has to be bounded on L2. And then if you want to study the regularity problem for the Zego projection, you also have to be able to say that the difference between the original kernel and the kernel for the conjugate operator has some cancellation. Some magic happens. Compactness, smoothing, whatever was, the kind of phenomena we have seen in one variable. And then, in the spirit of Calderon, Kaufman, McIntosh, and Meillet, you want all of the above to work for domains that have minimal regularity in some sense, that are as bad as you can afford them to be. So, all the steps have been carried out in the situation when the domain is smooth. And smooth in higher dimension means 3 continuous derivatives of the function that defines the domain. And it satisfies certain natural geometric requirements. And so the theory in this case is by now classical. It was established by Gerstmann and Stein on the very same year when Calderon proved L2 regularity for the Cauchy integral of a Lipschitz curve. Now, in higher dimension, the threshold for this theory is the class C2. And I will say a couple of words in a minute. So from now on, I'm going to relinquish any hope, because we don't have time, to look into the cancellation conditions that would give the solution to the regularity problem for the Zego projection. And I will just focus on the first 3 questions, which have purely to do with the Cauchy integral. And I'll remind you what they are. So we are now in 2 or more complex variables. And our goal is to find a 2 or more variables analog of the Cauchy kernel. I'm sorry, the domain there is in Cn now, and the boundary is in Cn. And this has to be meaningful when the point is in the interior of the domain, and holomorphic as a function of Z. So you can see that this expression, if we're now in the plane, okay, this is just my one-dimensional board. This expression, which is meaningful in one variable, is not meaningful in 2 variables, right? Because if you have a vector, what is 1 over a vector? So now in one variable, there's a trick. Another way of saying or thinking why one variable is such a beautiful place in the world and 2 variables is not. If you multiply and divide by the complex conjugate, you get something like this. And now that expression makes sense in any dimension, right? The problem is that if you want to make sense of that expression, and it's sort of a miracle of one variable that this is in fact analytic in Z, because you do that simplification, right? But if you want to do it in more than one variable, let's say in 2 variables, then you would have to contend with objects that look like this, say. And then let's say at the moment I am just let me see, DW2, DW2 bar, DW1, for example. And then, yes, and then you would have to, to make things symmetric, you would have to do something like this. And then you would have DW1, DW1 bar, DW2. So now your boundary, you're in 2 complex variables, that's 4 real variables, so your boundary has 3 real dimensions. And so integration against the boundary means you need to work with differential forms of degree 3, as opposed to the degree 1. And now, what is the problem with this formula? Here you had this magic simplification in dimension 1. Here you don't, because down here you have the sum of 2 components, and so you cannot simplify. So this kernel, which is universal and has its own merit, is not holomorphic in Z, and you cannot use it for studying the Szego projection. And then, of course, we haven't found a kernel yet, but even if we did, we want to be able to deal with minimal boundary regularity, and then we want to show that the operator, resulting Cauchy-type operator, is bounded in LP, or at least in L2. Hopefully it's a Calderon-Zygmunt operator, so you recover the full interval. And this is where we're going to swipe 40 years of hard work into one slide. So what is the effect of the requirement that your kernel must be holomorphic as a function of Z, which doesn't allow for that construction? Remember, we're trying to mimic the Cauchy kernel dynamics, right? So you want a kernel that's holomorphic in Z in the domain and singular when Z equals W. So that means that your domain D must be the maximal domain of analyticity of that function for each fixed W. And this is equivalent to the geometric requirement that the domain be pseudoconvex. This is a problem that was posed by Eugenio Elia Levi in the early 1900s. He died in World War I, so very early 1900s, to geometrically characterize the domains in 2 or more complex variables which are not the, or are the maximal domain of domains of analyticity for some analytic function. Any domain in the plane is pseudoconvex. And here is your analytic function. W is a point in the boundary that you have fixed. But already in 1906, Hartogs discovered very simple examples of domains that satisfy extension phenomena. Any function analytic in those domains has to extend beyond, and therefore the domains cannot be pseudoconvex. I'm not going to draw pictures because drawing pictures in 4 variables is a non-trivial affair. So where do we know that things work? So pseudoconvexity, which we now somehow accept at a meta level, comes in many flavors. There are many different notions of pseudoconvexity. One of them is the notion of strong Levy pseudoconvexity. And so Kurtzman and Stein, this is the classical theory I was referring to, Hanking Ramirez, were able to deal with the situation when the domain is rather smooth, three continuous derivatives, and strongly Levy pseudoconvex. So they were able to produce a kernel. I'm not showing it to you because it would take a lot of space to write it down, but I will show you another kernel later. What is interesting is that their proof of LP regularity somehow mimics the argument that we had here in higher dimension. And it mimics it in the following way. There is a model domain which is no longer the upper half space, but rather the Siegel upper half space. And there is a canonical operator on the Siegel upper half space, which is the analog of the Hilbert transform on the real line, for which you can prove LP regularity by direct inspection, because everything is very explicit. And the original operator on the original domain that you want to work with can be thought of as your model operator on model domain plus an error. And if the domain is smooth enough, you can forgo of the error, and you have your proof. And that's exactly the argument that Kurtzman and Stein were able to implement in the classical stages of the theory. It took us 40 years, from 1978 to 2016, give or take a year or two, to recover the same result of LP regularity for domains that are just 1 order of regularity less than the classical setting. So the assumptions here are all the same as the classical setting, except that now you have regularity 2 as opposed to regularity 3. And the reason why it took such a long time is because C2 is precisely the threshold where the original method of osculation fails, and you need new technology. And the new technology goes by the name of TO theorem, for those of you who have heard this kind of lingo. But I'm going to say nothing about that result, and I'm going to focus on another result, which is a little earlier, is 2 years earlier, because that's a result for which I can write the kernel taking only one slide. And so this is the situation when the domain is less regular, of class C11, so you don't have 2 continuous derivatives. You have one continuous derivative and then a Lipschitz second derivative, gradient, L infinity, second derivative. And you have some geometric condition, some other notion of pseudo-convexity. So what this notion corresponds to, and this is where I envy my colleagues who are taller than me. So what is strong linear convexity? This is our domain. We are now in 2 or more complex variables. This is a point on the boundary of the domain, the topological boundary of the domain. And so you have a tangent space at that point. And the tangent space can be thought of as a 2n minus one-dimensional vector space. And so inside that tangent space, you have a maximal subspace which has 2n minus 2 real dimensions and has a complex structure. If you take a point on that subspace and multiply times the imaginary unit, you don't get out of the space. That is known as the complex tangent space at W. And so what the condition of strong linear convexity says is that if your domain is strongly linearly convex, you can always separate your domain from the complex tangent space by way of a quadratic paraboloid, okay, with whose opening does not depend on the choice of boundary point. It's a separation result. So the good news is that there are relatively simple examples of strongly linearly convex domain which are not strongly convex, because it's very easy to see that their boundary contains a line. And so for this category of domains, we can actually produce a rather simple, in fact, the simplest known instance of Cauchy-type kernel, and it's known as the Cauchy-Leray kernel. And I have, the specifics of what that formalism means. You can read it for yourself. But this was first introduced in the 1950s by Jean Leray, who surprisingly studied it primarily for convex domains. But the notion of linear convexity was known about 15 years early in 1935. But people didn't realize that those domains support a Cauchy kernel. It was Leray who did. All right. So what are the good news? Well, any candidate for a higher dimension Cauchy kernel should better reduce to the Cauchy kernel in one dimension when n is equal to 1. And the good news is that this one does it. It's easy to see. Here we're using the fact that the gradient of rho doesn't vanish along the boundary, so you don't run into the 0 over 0 indeterminate form. Also, if you think of it as a function of z, that in fact is a rational function of z. It's the reciprocal of a polynomial in z. And so it's analytic as soon as holomorphic as soon as you can establish that the denominator does not vanish when z is in the interior. And this is where the separation property with the paraboloid helps you. Z is inside and W is on the boundary. So you have a kernel that has those two main features of the one-dimensional. But let me give you a little bit of a sense of what's the trouble when you try to study these problems under minimal regularity assumptions. So suppose now that your domain is not of class C2, it's only C11. What's the enemy there? The enemy are those two derivatives in the numerator. Because what you know is that your function is of class C11, so its second derivatives are in L infinity. This is the Rademacher theorem, or rather one iteration of it. So in particular, the second derivatives are defined only almost everywhere in W. But the topological boundary of your domain, which is where you're computing the second derivatives, has 0 measure. So in principle, the numerator could be undefined on the boundary. And here is the toy example that kept us awake at night for many nights. And there is no need to go on 2 derivatives. Let's just stick to 1 derivative and the classical Rademacher theorem. So your domain there is half space, negative x, right, in 1 dimension. And your function of 2 variables, f of x plus iy, is just the absolute value of x. The domain is clearly smooth. It's a half space. It's a half plane. And f is obviously Lipschitz. So Rademacher tells you that its gradient, these partial derivatives in x and y, are in L infinity. However, when you compute the restriction of the gradient to the boundary of that domain, you run into trouble, because you're differentiating the absolute value, and then you're taking x equal to 0. It turns out, however, that if you take a closer look at that gradient, you're into trouble only for one of those 2 derivatives. The y derivative of f is obviously well defined, and it is equal to 0. And it just so happens that the y derivative is the tangential, is the derivative in the tangential direction to the boundary. Whereas the problematic derivative, the x derivative, is the derivative in the normal direction to the boundary. And so it turns out that the tangential derivative of the gradient is meaningful, and that, in fact, is all you need. And it's also a phenomenon that happens in general. If you try to integrate 2 derivatives of a C11 function along the boundary of a C11 domain, what you're really doing is taking their tangential components, and there is a nice integration by parts that you can make so that the expression on the left is perfectly meaningful. And that's very useful because it tells you that the kernel is well defined in these minimal regularity conditions, and you have a Cauchy formula, and also it doesn't depend on the choice of function that you use to describe your domain, because you can have more than one. And so here is the theorem. The theorem is that for domains that are strongly linearly convex with minimal regularity boundary class C11, you do have a Cauchy-Euler integral which is well defined, and it is bounded in LP for P in the full range with respect to a special measure that is nothing but the numerator of your kernel, but in fact, under our assumption, is equivalent to induced Lebesgue measure. Okay, so the theorem goes, the proof goes by the application of this technology that I was mentioning before, the T of 1 theorem, in the easiest possible setting for those who are familiar with the jungle of T of 1, which is when T of 1 is 0 and so is T star of 1. Applied to a space of homogeneous type, which we think of as the infrastructure that is needed to state the theorem, which is informed by the geometry and the regularity of the ambient domain. The support is the boundary, the quasi-distance is essentially the denominator of the kernel, and the measure is the numerator. So, what does the T of 1 theorem say? I don't want us to spend any time losing our minds on this, but it just says, suppose that you are into your well-placed infrastructure, your good space of homogeneous type, which we have, and suppose that your integration kernel is singular, but you can control the amount of singularity. See, there is this negative exponent here. You know exactly how this blows up to infinity when W tends to Z. And if this kernel were differentiable, which it may not be, but if it were, then you would also have to be able to control the singularities of its derivatives. If you take this distance, W to Z, and you move it to the other side, you see that you get essentially difference quotients. And you're saying that this difference quotients can blow up, but you know no more than what you have on the right-hand side. And then there are some other technical questions you have to check. Essentially, you have to be able to prove by hand that the result you want is true for a special family of test functions where everything can be more explicitly determined. And then you have this even more technical conditions, the cancellation conditions, you have to compute your operator on two special functions and verify that they have the property of being of bounded mean oscillations. So under all of those conditions, if all of those are met, the operator is bounded in L2. And I point out that this theorem was needed to prove L2 regularity of the Cauchy integral in one dimension for a Lipschitz curve in its most general form, which is that. So what is interesting about the Cauchy-Leray integral is that, okay, there you go. Our kernel is precisely the denominator of the Cauchy-Leray kernel, and it has all the meets all the properties of the T(1) theorem. But what is remarkable, but that's again Cauchy formula spring into action, the Cauchy kernel reproduces analytic functions. 1 is the most analytic function you can think of. So C(1) is 1. And you can easily, in an elementary way, modify C to another operator T that satisfies T(1 = 0. What is remarkable is that there is no Cauchy formula for C star. The adjoint of the Cauchy integral is not the Cauchy integral. It's not self-adjoint. That would be the Szego projection. And so the reason why we work with this special Leray-Levy measure instead of the induced Lebesgue measure is because with respect to that measure, you can compute the adjoint and realize that it has this nice property as well. So I just want to say one word about the proof. The reason why everything works out in such a nice way, we apply the T(1) theorem in its simplest form, is because the Cauchy-Leray kernel is essentially a derivative. In other words, it is almost an exact differential, except for a remainder which is negligible. And the same is true for the kernel of the adjoint. Now, what's important is that once you establish that it is essentially an exact differential, it is the differential of a form, think of it as a function, if you will, which is less singular than the original kernel, because that's what happens when you take a singular function and differentiate it, you make it worst. So if you anti-differentiate it, you make it better. But you make it so much better that you can use this gain to show that the boundedness on the special space of test functions happens. So you might wonder, all right, you just told us that you need the same kind of theorem to prove the LP regularity of the Cauchy integral for a Lipschitz curve in dimension 1. Can we apply the same simplified version when T(1) is 0? Well, if you go back to the Cauchy integral, the Cauchy kernel in dimension 1, you can express it as an exact differential. In fact, with remainder 0. But the problem is that the form, or rather the function in this case, whose differential your kernel is still too singular. The log has too much of a singularity to be of any use in proving the hands-on proof of the L2 regularity on the test functions. And that's the reason why, in the one-dimensional case, you need the more general form of T(1) theorem, which you don't in higher dimension. And I just want to say that the two assumptions of strong linear convexity and C(1) regularity are optimal. And what is surprising is that you find counterexamples by simply taking a ball, which is the most perfect place in the world to study the Cauchy integral even in higher dimension, and just flattening it a little bit in the first instance, which gives you a smooth domain which is no longer strongly linearly convex, or squishing it a little bit to a pear-shaped form, so to speak, which gives you a strongly convex and therefore strongly linearly convex domain, which is, however, no longer of class C(1)(1). It's only of class C1 alpha for alpha less than 1. And in both cases, the LP regularity crashes for the integral. So, very short summary. We had those three questions at the very beginning. In dimension 1, is there another integration kernel that retains the main assets of the Cauchy kernel? Yes, the Szego kernel for a planar domain, which satisfies a good transformation law And so even though it is not universal, you can still compute it. And of course, you know it as well as you know your conformal map. But there is a lot of technology for that. And there is also a conformal map-free approach that you can use to study the LP regularity problem for Szego. If you go to higher dimension, the question we were asking was, is there a holomorphic analog of the Cauchy kernel of 1 over W minus Z that retains the main assets of the one-dimensional theory? Yes. For instance, the Cauchy-Leray kernel. However, it is irretrievably domain-specific. You cannot, because there is no transformation law that allows you to move it to other domains. But there are other kernels that are known when the Cauchy-Leray kernel doesn't apply. Of course, I mean, the theory is very extensive, but there are other such kernels. And now, in any dimension, do the answers to the questions that we have posed above depend on the analytic properties or the geometric properties of the underlying domain? And the answer is absolutely, as we have seen. In any dimension, they depend on the amount of regularity of the domain. The amount of regularity gives you the p size of regularity for the Szego projection, for instance. And in dimension 2 and higher, you not only have to worry about the regularity of the domain, but also the shape, the amount of convexity that it satisfies or fails. And with this, and seeing that I have definitely overstayed my welcome, I'll just say thank you.
So the Cauchy kernel is intimately related to the fundamental solution of certain differential equations, namely the Laplace's equation. Can something similar be said about those other kernels of the Szego kernel?
The Monge-Ampère. People have asked similar questions, and that's where you get, yes. Monge-Ampère equation, the Debarbee equation, which is a specialized version of the Debarbee problem, but restricted to the boundary of the domain, where you're differentiating, you're computing Debarbee with respect to tangential derivatives. So, yes. And it's one of the reasons why it is such a fundamental kernel in several complex variables.
Which brings the question, does PD methods give complementary results? Because as you mentioned, the fully harmonic function
Yes.
is the real part, imaginary part. Has
Yes.
someone studied the PDE for those and able to say something about?
As far as I know, only the Monge-Ampère equation. And it's been studied, it is being studied by people who work in pluripotential theory. Eric Bedford at Indiana, for instance, has been one of the main contributors, or my colleague, Dan Coleman. But I feel that this sort of PDE side in several complex variables has not been pursued to the extent that I see, as you know, I'm visiting here for a few months and talking with all of you, has been pursued to the same extent as the one variable side. And I guess, you know, the main reason might be that you guys work with concrete applications that you have in mind, and you model the problem using, you know, these functions, whereas the traditional approach in several complex variables is that you're not looking for a model, you just want to look for the most complicated or the most general and the most sophisticated or the least regular setting where you can still carry out analysis. And so the applications somehow can be sidetracked.
More questions? Or then I have questions. So I believe I already asked about the Sahotsky-Flemish formulas in the previous lecture, but maybe you can comment a little bit more. And the second question relates also to the analog of the Cauchy kernel. In theory of single integral equations, very important to find asymptotic, even the first term of behavior of Cauchy kernel when the density has like power singularity or some other singularity. So if you have a domain, what just happens at the edge? Yeah,
so there is a whole lot that I haven't said. So this strategy of comparing with the Cauchy kernel to study the Szego projection is sort of a more recent approach. But prior to that, people knew about the Szego projection for a long time, of course, I mean, back to Hardy's days. So the strategy was exactly to study the asymptotics of the Szego kernel. And people like Charlie Pfefferman have done a lot of work, or Duong Fong at Columbia. The problem is that the kernel asymptotics require a lot of regularity, more than C3. They require C infinity. And so if your goal is to reduce the regularity, then the kernel asymptotics are not known to bear any fruit. Yes, but that's been, historically, it has been the first approach. I can point to some papers. I have to confess that I don't remember the other question that you asked.
The question was about the Flemish of Sachowski.
Yes, yes, yes. So there is a version of, so you're asking whether there is a Flemel formula for instance, the Cauchy-type. Yes, 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 there is, and it has not been pursued.
Oh,
Yes.
Yeah, the question was about possible generalization of Flemish formulas for higher dimension, M2 and higher, even if the surface is perfect without any irregularities.
So people have studied this kind of questions from the point of view of the ability to extend beyond the boundary, or if you have a function that's just defined on the boundary and you want to extend it on one side or the other. But I think this has been done mostly, and you can ask Irina Mitria, who is an expert on this. It has been done mostly on for the Bochner-Martinelli kernel. Not as much, as far as I know, for Cauchy-type. Part of the problem is that this approach of viewing the question as a Riemann-Hilbert problem hasn't been really pursued in higher dimension. Or at least it's not a mainstream line of investigation. I know of one paper that Elias Vigert pointed out to me when he was here in September, of one extension problem, something to do with a function defined on a hypersurface and extending it holomorphically or in a CR way beyond, by viewing it as a Riemann-Hilbert problem by a mathematician in Yugoslavia. But I can't, that was the only instance that I knew. And it doesn't use the Cauchy-type formalism. It's a different setting.
Okay. So if no more questions, then thank you.
Thank you.